What's up, guys? My name is Vincent, and today I want to show you all how to find the area of a region formed by a polar curve. So we have three examples, but for the first one, we're finding the area of the region enclosed by one loop of r equals sine 2 theta, which is a rose curve. This is just a rough sketch, and the formula that we're going to use is here. And the way we use this formula is we have to determine which two angles enclose the region that we're interested in. So if we look at this question here, if we're trying to find the area of one loop, we could pick any of the four loops, but let's say to make it simple, we'll just focus on quadrant 1 here. So we want to find the area of this section here that I colored in red. So the two things we have to know are the angles. Now, let's say sketching this thing is a little bit tricky. One way of finding the angles that you're interested in is by setting the function equal to 0. Because this region starts at the origin, the radius extends outward, and then the radius comes back to the origin. So we have to find out at what two times is the radius equal to 0. So if we set sine 2 theta equal to 0, well, we think when is sine equal to 0? When the argument or the term on the inside is equal to 0, which would mean theta equals 0. Or if we're taking sine of pi, 2 pi, 3 pi, or any negative integer like negative pi, negative 2 pi. So if we set the argument equal to pi, we would also have theta here equals pi over 2, which shows the two angles that we're interested in. Because between theta equals 0 and theta equals pi over 2, we have one loop. So when we want to use the formula, in a sense, this is theta 1 and this is theta 2. So we just found the two limits of integration here. So now we just plug into the formula. We've got the area is equal to 1/2 the integral from 0 to pi over 2. And now our function is sine of 2 theta. And this function is being squared. But for the questions we're dealing with, a lot of times we can make use of symmetry. And if you notice that this line here at pi over 4, this line cuts this petal directly in half. So if we want, an alternative way to evaluate this would be to multiply, or maybe I'll just put the times 2 in front. We would have 2 times the integral, but then instead of going from 0 to pi over 2, we could double the integral from 0 to pi over 4. Because this area here in green is half the total area. So if I double it, it would give me the area of one whole petal. So we could make use of this to make this question simpler. So if we double this integral, we just have to change the limits from 0 to pi over 4. And then when we square the inside, we have sine squared of 2 times theta. And we have our d theta like this. And the benefit of that is that now the 2 times 1/2 cancels out. But to close this out, we need to make use of the trig identity for sine squared theta. So in general, maybe I'll use sine squared x so you can see it. This is equal to 1/2 1 minus cosine 2x. So we're going to apply this trig identity here. And we'll see that the sine squared 2 theta can be expressed as 1/2. And now we just rewrite our integral from 0 to pi over 4. And on the inside here we have 1 minus, but we have to be careful. We're not going to write cosine of 2 theta because the argument is already 2 theta, so we have to double it. So it's going to be 4 theta. And we write our d theta at the end. So we'll get rid of this now. We don't need this. But now we're ready to take the antiderivative. So we have 1/2 first, and now we'll just take the antiderivative term by term because they are attached by subtraction. The antiderivative of 1 is just theta because we're doing the integral in terms of theta. And then the antiderivative of cosine 4 theta is sine 4 theta divided by 4. So we'd have 1/4 sine 4 theta. And anytime you're unsure if you did the antiderivative correctly, just take the derivative of your answer and you'll see that it matches the integrand. And then we just have to write our limits of integration here. So then the last thing to do before we close out this problem is just to evaluate this at the endpoints. So we have 1/2, and we'll need some parentheses here. So we've got pi over 4 minus, and we have 1/4 sine 4 times pi over 4 is pi. And sine of pi is 0, so this term is already gone. And now when we substitute in 0, we'll have 0 minus 1/4 sine of 0, which is also 0. So the only term that survives here is the pi over 4, and if we multiply 1/2 times pi over 4, that's going to give us pi over 8, which is our solution to the first question here. For the second question here, we're doing the same thing, except now the function is r equals 3 cosine 5 theta, which, if you know your rose curves, this has 5 petals. Anytime the coefficient of theta is odd, that tells you how many petals there are, and when it's even, you double it to find the number of petals. But I'm not going to spend the whole time here sketching this curve. Remember, all we need to know is the area of one loop. So we just have to find the area of one petal. And remember the concept. In order for us to construct a petal, we're starting at the origin, we're going away from the origin, and then we're coming back. So that means we have to find out at what 2 points is the radius equal to 0. Well, 3 cosine 5 theta is equal to 0 when the argument is equal to some multiple of pi over 2. So if we look here, since cosine of pi over 2 is equal to 0, we're going to set 5 theta equal to pi over 2. And that tells us the first point where the radius is equal to 0 would be at pi over 10. And pi is 180 degrees, so 180 over 10 is 18 degrees. So roughly 18 degrees would be somewhere here. So we're not drawing this necessarily to scale, but this is roughly where our angle is. But then what we could also note is that cosine of negative pi over 2 is also equal to 0. So if we set 5 theta equal to negative pi over 2, then we would have theta equals negative pi over 10. So if we sketch negative pi over 10, it's going to extend here into quadrant 4. And what this tells us is it tells us the location of one of our petals, that our petal for this rose curve, 1 out of the 5 is going to be between pi over 10 and negative pi over 10. Let's just label this line here. Okay, so now that we have everything set up, we have our limits of integration, we could go ahead and set up the integral. So we're going to have 1/2, and now this time we could expedite this. Instead of going from negative pi over 10 to pi over 10, we could use the same concept as before and cut this at the halfway point. From 0 to pi over 10 would give us half of a petal. So if we double that, it'll give us the area of a whole petal. So what we could do is we could do 2 times the integral from 0 to pi over 10. And we write our function on the inside. So once again, we're using this main formula here to find the total area. However, we're making use of symmetry here, that from 0 to pi over 10 is half the total area, so that by doubling the area from 0 to pi over 10, we'll get the entire petal. And now we just write our function on the inside. We have 3 cosine 5 theta, and this quantity is being squared, and we have d theta here. So then to work this out, first we'll simplify a bit. We have 2 times a half going away. the inside, we have 3 squared is 9. So we'll just take the constant outside the integral, and we're going from 0 to pi over 10. And we're left with cosine squared of 5 theta d theta. But now, once again, we're going to have to make use of a trig identity. And we're going to make use of cosine squared x equals 1/2 1 plus cosine 2x. So this is a formula we're going to apply here. So our integral, we could rewrite it as 9 times 1/2, and we'll write our limits in, 0 to pi over 10. And our inside here is 1 plus cosine, and we're doubling the argument, so 5 theta is going to change to 10 theta. And then we write our d theta. So we don't need this formula anymore. So then we are ready to take the antiderivative here. We have 9 over 2, that's our constant, we're just going to take out. We're just combining this 9 and this 1/2. And now the antiderivative of 1 is equal to theta. And now we have the antiderivative of cosine of 10 theta is 1/10 sine of 10 theta. And remember, at any point, if you have to, if you want to check your antiderivative, just take the derivative, use the chain rule here, and it'll bring you right back to this integrand. And we're going from 0 to pi over 10. So now we just make our substitution. We have 9 over 2 we'll leave on the outside. And we've got pi over 10 plus, and then we have 1 over 10 sine, and then 10 times pi over 10 is pi. So this term is going to go away. And then we've got minus, and when we substitute in 0, we've got 0 plus 0. So the first term is the only one that remains, and we're going to have 9 pi over 20. This is our solution to the second question. Okay, for the last question, we have something a little bit more complicated. We have a Limaçon with an inner loop. So for this function, we'll just get a sketch. But going in the direction of 0 radians, we would have 1 plus 2 sine 0, which would give us 1. So we'd go out 1 unit this way. In this direction, if we're looking in the direction of pi, we would have 1 plus 0. So we're going 1 unit this way. Looking in the pi over 2 direction, we would go 1 plus 2 sine pi over 2, which would give us 1 plus 2 is 3. And then this one's probably the trickiest when we're looking at 3 pi over 2. So we're looking south. We have 1 plus negative 2, which is negative 1. So facing this way, we have to go negative 1, which brings us to the point 0, 1. And since 0, 0 is a point on this curve, we include this point as well. This is one of the more efficient ways of sketching a Limaçon with the inner loop. So it's going to look something like this. It's going to go up here, goes down, and then the inner loop goes from 0, 0 to 0, 1. So the area that we're interested in is this little space here. But for these kind of questions, the most important thing that you have to be able to find is you have to know what are the two angles. And when we think about it, the radius starts out greater than 0, but then eventually as we turn to trace this Limaçon, the way we generate this inner loop is that the radius, first it equals 0, then the radius is non-zero, and then the radius goes back to 0. So what we want to find is, when is the radius equal to 0? What are the 2 times the radius is equal to 0? For what values of theta? So if we set the function 1 plus 2 sine theta equal to 0, we rearrange this equation, we'll get sine theta equals negative 1 over 2. And if we're solving this trig equation, we'll look for solutions from 0 to 2 pi. Sine is negative in quadrants 3 and 4. Now, the reference angle we would have here would be pi over 6. Sine of pi over 6 equals positive 1/2. But if we're interested in quadrants 3 and 4, then the two angles of theta would be in quadrants 3 and 4. So we have to say what angle has a reference angle of pi over 6 in quadrant 3. It would be 7 pi over 6. And then in quadrant 4, it would be 11 pi over 6. So these are our limits of integration. That's when we begin this inner loop, and that's when we end it. We begin at 7 pi over 6, and the loop ends at 11 pi over 6. So now we just plug this into the formula. So we have the limits here from 7 pi over 6 up to 11 pi over 6. And it's 1/2, and we're squaring the function 1 plus 2 sine theta. So what I'm going to do, I guess kind of quick, is if we're squaring 1 plus 2 sine theta, the first term, 1 times 1 is 1, and then we'll have 1 times 2 sine theta. We'll have another 1 times 2 sine theta. So 2 sine theta plus 2 sine theta is 4 sine theta. And then the last term would be 2 sine theta times 2 sine theta, which is 4 sine squared theta. Now for a question like this, the rest is kind of annoying, but we'll go through it anyway. We'll pretend that a calculator is not an option. But what we're going to do is we're going to apply the trig identity to the sine squared theta again. So we have 1/2 the integral from 7 pi over 6 to 11 pi over 6. And what we have is 1 plus 4 sine theta plus 4 times, and we've got 1/2, 1 minus cosine 2 theta. We'll just shrink this down so we have space. Okay, we'll throw our bracket on, and let's make sure the colors match. So we'll throw this bracket on, and then this is times d theta. So then to close this integral out, first we'll simplify. 4 times 1/2 is 2. So we'll just clean this up a little bit. This is going to be 1/2 times the integral from 7 pi over 6 to 11 pi over 6. And what we have on the inside here is we're going to have 1 plus, and then if we distribute this 2, we have 2 times 1. So I'm going to have 1 plus 2 is 3. This is the only sine theta term, so we're going to have a 4 sine theta. But now we have to think about what we have last. We have 2 times negative cosine 2 theta, which is negative 2 cosine 2 theta, and we have our d theta here. So then to work this out, we're just going to find the antiderivative. So we've got 1/2, and let's just make space. We've got 1/2, the antiderivative of 3 is 3 theta. The antiderivative of 4 sine theta is negative 4 cosine theta. And then the antiderivative of the last term is minus sine 2 theta. Remember, at any point when you want to check if you did the antiderivative correctly, you could just take the derivative of your answer. And you just want to be really careful with these sign changes here. And for the last one here, you want to be careful of the 2 theta, that when you're taking the antiderivative, that you also have to divide by 2, which wipes out that coefficient of 2. So then here, all we have to do to close this out is substitute. So we got 1/2, and we'll throw a bracket. We've got 3 times 11 pi over 6, which is 33 pi over 6. And we've got minus 4 times, and this is where we want to be a little careful. This is a quadrant 4 angle, and this is a quadrant 3 angle. So if we were to make a substitution here, 4 times cosine of 11 pi over 6, I think of 30 degrees, and cosine of 30 degrees is square root 3 over 2. And since we're in quadrant 4, where cosine is positive, we have negative 4 times positive root 3 over 2, which is negative 4 root 3 over 2. And then here, this is where we have to be a little careful, is there's a 2 theta here. So when we make the substitution, we've got sine of 2 times 11 pi over 6 is 11 pi over 3. So then when we are evaluating this here, we have to think about the argument is pi over 3, or 60 degrees, which would give us a term of root 3 over 2. But then we have to think about where does 11 pi over 3 throw us, in which quadrant? Well, before I just said 60 degrees, and 660 degrees, if we subtract 360 degrees, puts us at 300 degrees, which would put us in quadrant 4. So in this case here, this is going to work out to a negative root 3 over 2, which would change this to a plus root 3 over 2. So just a few ways of, if you're doing this without a calculator, how to do that reasoning. So we could go ahead and change this here to a plus square root 3 over 2. Now we have minus, and when we substitute in 7 pi over 6, we've got 3 times 7 pi over 6 is 21 pi over 6. For this term here, we've got minus 4 times cosine of 7 pi over 6 is a quadrant 3 angle. Cosine is negative in that quadrant, which is going to change this to addition because we have a negative times a negative, and the term is still going to be square root 3 over 2 because the reference angle does not change there. But now for the last one, we have to be careful all over again. Now we're looking at 7 pi over 6 times 2, which is 7 pi over 3. And if we think about 7 pi over 3, 60 degrees times 7 corresponds to 420 degrees. So if we subtract 360, this corresponds to a 60-degree angle, which is in quadrant 1. So sine is positive at this angle. So we would have minus sine of 7 pi over 6 is going to be just square root of 3 over 2. But since there was no sign change here, we have a negative times a positive, this is going to work out to minus square root 3 over 2. So with these questions, you may get a calculator, but otherwise you just have to be really careful with determining if there's going to be a sign change, because the most common mistakes here tend to happen in this section here when you're subtracting. So just be very careful at this part. So now we got 1/2 times, and if we work them out term by term, 33 pi over 6 minus 21 pi over 6 is 12 pi over 6. 4 over 2 is 2, and 4 over 2 is still equal to 2. So we've got negative 2 radical 3 minus 2 radical 3, which is negative 4 radical 3. And then here we have square root of 3 over 2 minus negative square root of 3 over 2, which is a positive 2 square root of 3 over 2. So the 2 over 2 cancels. And now to simplify this, we've got 1/2. 12 over 6 is 2, so we got 2 pi. Negative 4 radical 3 plus radical 3 is negative 3 radical 3. So then the final answer here, to simplify, distribute the 1/2, and you'll have pi minus 3 radical 3 over 2. Okay, well, this is going to conclude this video on finding area determined by polar curves. If you found this video helpful, please click like and subscribe below. It helps me grow this channel. And if you have any requests for future videos, leave it in the comments section below. And thank you for watching.